Maxim, and I'm from Linaro's toolchain working group. Today, Yao Qi, who is an assignee from ARM to Linaro toolchain working group, will be telling us about the state of GNU debugger, GDB, for AArch64 and AArch32 ARM architectures. Yao is a long-time GDB developer and GDB maintainer.
Thank you. Good morning, everyone. As Maxim introduced, my name is Yao, and I've been working on GDB for several years. And okay. Yes. Here is an overview of the GDB development specific to ARM and AArch64 in 2015. And you can see there are, here is a timeline. And on the timeline, you can see there are several interesting, useful features added into the GDB to support the AArch64 and ARM, like the syscore catch point, reverse debugging, tracepoint, and NonStop debugging, display stepping, something. Before 2015, I think the AArch64 has already, has been added into the GDB, but these features are missing. So in the last year, we add a lot of new features to compare with x86 into GDB. So as you can see, the GDB commits to these target specific files increased dramatically since last year. That is a good sign.
So I have a question for the audience. Who knows what trace points are? Who knows what are the other features mentioned on the slide, but it's quite difficult to see the text. Yeah.
Okay, anyway, I will go through all of them one by one in my following features slides. Okay, the first one is reverse debugging. Reverse debugging was added into GDB many years ago, and only x86 is supported. So several years ago, someone, I don't know, to add the support for ARM. And last year, we added this support for AArch64. Reverse debugging, that is a very, very fancy topic, which means you just start the record in which GDB can record the processor and the memory state after the instructions after the execution of the instruction one by one. And when you want to reverse execute the program, GDB will check the log it recorded just now and reverse the program state so that the program can be executed in the reversed order. So there are some new GDB commands. Say, in the forward execution, you use the continuous step and the next and the finish. In the reverse debugging, you just use the reverse, continue, reverse step, so the program can execute in the reversed order. That is to be honest, the design of I think the feature is very good, but the design is a little bit very simple and a little bit naive, I'd say, because all the instructions, they should be decoded and recorded into a history, which means if you record some shared library like the C library or something, if the program is called a printf, which means GDB has to record many instructions. As a result, it will they will consume a lot of memory because all the histories are recorded in the memory. So that is a drawback of the design. But anyway, I think that is still useful in some cases. So that is the reason we add this feature, support the AArch64, and that is pretty good nowadays.
Who have used reverse debugging? One. How slow is it, the question?
How slow? Okay, yeah.
Stepping through a large sub-function call.
Well, yeah, if your host machine has a huge memory, that is okay. But if you
But still, you're decoding every instruction. So is it 1/100th real time or 1/1000th real time? Or?
yeah, I think so for the instruction decoding, it should be fast enough. But it will record all the, say, for every instruction, GDB have to decode it and see which registers are changed and which memories are changed. All such information will be recorded in the history. That should be very fast, but it will consume a lot of memory if there are so many instructions to be recorded. That is what I mean slow.
Is it offline playback kind of thing, or is it something that you actually run on the host?
That is not an offline thing. That is you can turn on the reverse debugging on the fly if you recorded the history, and you can turn it off and continue to do the forward execution. That is not offline things.
All right, so what we were saying is that you go back in history and then start the execution again from that point.
No. Let me see how to go back. When you do the forward execution, which means nowadays the normal mode, all the instructions, the program is still executed, but in a very special mode. So the instructions will be executed one by one. The GDB decodes them and saves them into a repository or history or whatever. When you want to reverse, GDB just read the history from this repository. So the program is still there, but it is not, in fact, it's not executed. GDB read everything from the recorded history. So when you want to stop reverse debugging, GDB will just switch from reading history here back to the normal execution, so your program can continue forward executed.
Okay, thanks.
Okay, let's move on. The other thing we did is to add support the AArch64 for the NonStop Debugging. That is a very useful feature when you debug multi-thread applications. In default, GDB use all-stop debugging, which means, say, for example, if you are debugging a program which has 10 threads, and just one thread hits a breakpoint, GDB will stop all of them, which means all the rest of the next threads are stopped, which is not user-friendly. So for the non-stop debugging, which means if the one thread hits a breakpoint, just that thread is stopped. All other threads are still running, unless the user wants some threads to be interrupted or stopped. So that is very useful thing. And like in the all-stop and the non-stop things, like, so here is a flow that I can explain why GDB need to stop all the threads. Because say on the instruction 2, there is a breakpoint, and you want to continue, but the instruction 2 has not been executed yet. So GDB has to remove the breakpoint, revert the instruction 2 again, and a single step execute this instruction. And then write the breakpoint back again. So in this step, GDB has to stop all other threads to make sure at this moment no other thread is running. Otherwise, it is possible that other threads may go through this area but doesn't hit this breakpoint. So that is wrong. So GDB has to stop them. But as I said, the all-stop debugging is not friendly to multi-thread applications, just like like this picture shows on some motorway pay station. You know, all the cars have to stop and pay some money and go. So that it will cause a lot of trouble to the traffic. That is similar to when you're debugging multi-thread applications. Okay, yeah, NonStop debugging. So in order to support the AArch64 NonStop debugging, what we do is, as I mentioned in my previous page, so the problem here is when you step over a breakpoint, you have to stop all other threads. So if we do not want to stop other threads, what could we do? We can execute this instruction somewhere else. So say, here is instruction 2 on this place, and we do not, the breakpoint on the instruction 2 are still there, but we move the instruction 2 somewhere else to execute it, to make sure the effect of that instruction execution is still the same as the original one. So in this way, since the breakpoint is always inserted in the program, we don't have to worry about that. Some other threads may go through this area without hitting the breakpoint. That is what I'm going to talk about.
That's the next slide.
Yes.
Okay.
So that is the reason why the original instruction is instruction 2, but now here, there can be one instruction, and it can be 2 instructions, and it can be 3 instructions to achieve the effect of the original instruction. Yes. The interesting part of the display stepping is how to relocate this instruction to somewhere else and make sure the effect is still the same. Like the PC relative. Here are some example. Say here is this is a load instruction from some address to the register. But since you move this instruction somewhere else, the offset encoded instruction, I mean the original instruction, may be out of range. So you can do that. So GDB has to choose another instruction. Say, we can execute this instruction, but the GDB write the address value into the X0 and just execute the LDR WRX0 instruction. So the instruction is different. But the effect is still the same. And here is for the PC relative. If the offset, from the new location to the destination, it still can fit into the instruction encoding. GDB just modify that. Otherwise, we will use some different instructions, like something like this instruction to get the address from the register, and we can restore the register after that. Here is another example is I think that is the condition branch. During the, I think that still just has a problem of the offset, the offset problem. So if you move to somewhere else, the offside, it's too big to fit into the instruction. We have to use some other instructions. And like the BL, branch and the link. Since this instruction has some set effect, which means it will write the next address to LR. So if you execute this instruction somewhere else, and you still execute BL, which means the LR register is wrong. So in this case, we have to execute the B instruction without updating the LR register, but the GDB writes the LR register by itself. Yeah, so that is some. So I don't give all the instructions we have to care about, but just some examples, and here are some other instructions the GDB has to care about.
Are there cases that cannot be handled by non-stop debugging, or any instruction stream, any program with several threads can be handled by a GDB in non-stop debugging mode?
Sorry, can you repeat? You mean?
Are there programs that can't be debugged in this mode? So, or instruction streams, like there is instruction that you cannot patch out.
No, I think all the instructions can be patched out, as far as I can tell. Okay. Yes, Max.
So I've actually done this a number of years ago, but there were some instructions I just said, it's not worth doing this. I'll just make the register changes myself. And you're kind of doing that in the third case. You're letting the actual CPU do the branch, and then you're doing the link, right? So are there any instructions you just say, punt it, I'll just change the registers myself?
Myself, I mean GDB or program?
GDB, instead of, it just calculates what the output register would have looked like. It just does it. Right?
Yes, actually you have the, from the GDB's point of view, you have multiple choice. GDB can emulate all the instructions without executing any instructions somewhere else. Mm-hmm. Say GDB says this instruction in theory, we know the effect of this instruction. GDB can update the register, can write the memory, can do whatever we want. But that will be more difficult in the source code, which means you need to write the source code, in GDB, to do what the instructions does. Mm-hmm. But that is something combination. If the hardware can do that, in the display stepping, just let hardware do. Otherwise, GDB just can give some help. Mm-hmm. That is an implementation decision at the moment. We are very lucky actually. That is the display stepping for AArch64. If I give you the table for ARM, that will be maybe 10 times bigger than this table, because ARM is more difficult to handle these things. Yes, and let's go to the tracepoint. The tracepoint is a very useful feature if you just do some non-interactive things. The breakpoint was invented to do some interactive things. Say you set a breakpoint and run, and the program stop. You examine the status and see if something wrong or not. If nothing wrong, just resume the program, and that is what breakpoint does. Tracepoint does something differently. You just create the breakpoint and fire the tracing, and wait a while and stop the tracing. And then you can got the trace data from the GDB server and display the information collected by the trace point as at the moment. Or even better, you can dump the trace data into a file so that you can do the post analysis afterwards. And
Is it application level trace or system level trace?
that is a software trace for that specific process. That is not like the hardware trace or system level trace. No, it is not. It is just the program level trace implemented by software.
Because you can decode the trace. So can you use this GDB to decode the trace from other guys' trace hardware?
In theory, it can. This trace point are generated by GDB itself, so GDB can understand them.
Yeah.
But it doesn't matter. I don't think there is anything difficult, to teach GDB to understand the new trace source, like the hardware or whatever.
Is there
Should be straightforward to add that. But nowadays, GDB just insert its own trace point and collect data.
Okay, thank you.
Yes, and there is I think Eclipse CDT has some support for the trace point. So in the CDT, you can insert a trace point and show some data. That is done by Ericsson. Yes, for the trace point, two types of trace point and a fast trace point. Fast trace point is faster, and the trace point is slower because trace point is done by breakpoint. So which means there is on the operating system level, there is still a trap, and there is a process context switch from the program to the GDB server, and the GDB server do some collects and switch back, resume the program. The program can running. For the faster trace point, it is faster because we do not use break instruction. We use jump, which means the program cannot be interrupted. So the program just, when you set a breakpoint here, GDB server will insert a jump instruction and create a jump pad somewhere in the program's address space. So when the program come here, it will jump to the jump pad. The jump pad is to set up the stack and to save all registers and jump to some C program. And in the C program, we just do all the things defined by that trace point. Say the trace point want to collect some memory, want to collect some register, we can do the things here. After that, we will go back. So before going back, the instruction on the instruction tool is not executed yet. So like the display stepping, we execute this instruction here and jump back. So there is no interrupt during the whole process. Okay, please.
I just wanted to extend that here, essentially, trace point is an execution of a C function that can be anything. Like you can say that execute printf at this trace point and dump data to either a file or stdout or stdir.
Okay.
And then continue with the program without essentially any breakpoints hitting. Why doesn't it work in shared libraries, fast trace points?
Yes, here is what I want to say. Usually, the main executable is allocated on the lower space in the address space, and the shared library is allocated on the higher space. So when we allocate a jump pad, at the very beginning, we just want to allocate the jump pad as close to the main executable as possible. So, which means the jump pad is sometimes maybe a little bit far from the shared library. If you want to use a jump or branch instruction, due to the range allowed in the instruction encodings, sometimes the distance will be out of range. So you cannot jump from the shared library to a jump pad.
Also, is there a challenge with the shared library that if you are going to patch code inside the shared library, it will be applicable to all the processes that are using that shared library, that it is more difficult to change code segment of shared library than it is of application?
No, I don't think so. GDB doesn't have to worry about that. I think Linux kernel just map the code, the shared library to different processes. Once you want to modify the code, Linux kernel will give a different copy to you. So the only change will be, the effect is only within this process. Other process use this shared library shouldn't be affected. That is a kernel's job, as far as I know.
So why, it seems like you could, as you link each program and shared library, you could actually leave room for a jump table or create a jump pad in each loadable object. So that
Yes.
What's wrong with that?
Yeah, actually, that's still the design problem at the very beginning of the tracepoint in GDB server. At the very beginning, there is only one single jump pad. So we cannot have two jump pads, which is close to main executable and which one is close to the shared library. We cannot do that because GDB server has to know the start address of the jump pad. So if we have two, nowadays GDB server will be confused.
Does that mean you can only have one trace point?
Sorry?
Does that mean you can only have one trace point?
No. You can have multiple trace point, but you just one jump pad.
So the pad can contain multiple of these patches? Okay.
Yeah, but just in one area, you cannot have the jump pads in totally two different areas. That is a design limitation in the GDB server.
I guess the question is it an implementation shortcoming, or this potentially implementable to use multiple jump pads, one for executable and one for shared libraries?
I think that is an implementation limitation. Okay. Multi-arch. Multi-arch debugging, something like the on x86-64, you can have single GDB instance, which is 64-bit program, so that you can debug both 32-bit program and 64-bit program. That will be very useful. Since the AArch64 is also, you can run the ARM 32-bit program on 64-bit hardware, so we have the same requirement as well. In GDB, we call this multi-arch. So what is multi-arch? So say this is GDB, has some slot to the SD card. And the SD card is a big one, which is a AArch64 process. And the ARM process is a micro SD card, which is a small one. Multi-arch, in fact, is this adapter, which means you can insert the micro SD card into the adapter so that your micro SD card can be read by some SD card socket or something. So this is a multi-arch thing. There are a lot of work, cooperate with the kernel guys. They are very, very helpful to to fix some bugs, in Linux kernel, and to expose some new register sets for me, so that the GDB 64-bit GDB can read the 32-bit registers, and to do some you can also get the thread area from the Linux kernel, and the hardware breakpoint and watchpoint. All of those things you need the kernel support. GDB just read them and understand them. Yeah, and after all the bugs, all the features are added in the Linux kernel, we just do something, to refactor the GDB source code, and all the things, it's implemented that way. That is very convenient on the 64-bit. You just need one single instance of GDBs and debug different programs. And even you can debug both programs, 32-bit and 64-bit, in one GDB instance in parallel, which means you can both, in the same time, you are debugging two processes or even more, and they are different.
So can you actually load more than one executable into GDB process, into one GDB process?
Load one? Yes.
More than one executable?
Yes. That is something like inferior. So in each process is named inferior. So you can debug multiple processes in one time. In theory, you can use one GDB. You can debug all the processes on your machine if you have the permission to do that. Okay. So let's go look at something like the plan or something in my mind that we should do in the next this year. Some bug fixes in the reverse debugging, especially for ARM, because that was contributed by someone else many years ago, which was not very carefully reviewed. So there are a lot of bugs there. Kernel awareness, that is, we want to teach GDB to understand the Linux kernel threads rather than the user space threads. So that will be very useful when GDB is debugging Linux kernel through QMU or JTAG probe. That is one thing. Range stepping. Range stepping is very helpful to improve the performance in the remote debugging. So that will be very faster if this is done in some cases. And the tracepoint for ARM, will be being reviewed nowadays upstream. That is done by Ericsson. They want to do that, but there is something we are still reviewing the patches. Compile and inject code in GDB. I think this project, I think was started by Red Hat people, and I think they were inspired by LDB, which use clown library to parse expression. That will be very convenient. But in GDB nowadays, we are still, have to use the flex and the yak file by GDB itself and pass all the expressions by GDB. So the goal here is we use the libcc1.so, which is provided by GCC, and to do the expression parsing the way that LDB is using. Oh yes, the last thing is improve the GDB performance. I did something several years ago for x86. That is very useful, but I didn't do that for ARM and AArch64. But probably this year we can do something for ARM and AArch64. That will be very useful when you attach the GDB to some very slow speed JTAG probe. Sometimes someone complains to me that will be very slow if you do some operation like the disassembly or something. So the goal here is we want to speed up the operations like that. The general idea here is just to use a cache. So nowadays, the GDB just read everything from the JTAG probe from the GDB server. So if we can have some local cache to store these contents, so GDB doesn't have to read these contents every time again and again. Okay, that's all for me. So, any questions?
If you back up one slide. So you're talking about injecting code into the program.
Yes.
Is that like for a trace point?
Oh no,
that run?
No, that is different. That is say that is a higher level, and the goal of the project is you can write an expression in GDB command line in C language, and the GDB just compile them and inject this code into the program you are debugging and run that code, and you can see the result.
Immediate mode. You write an expression, it compiles it, it runs it,
Yes.
returns the results or produces the side effects,
Yes.
and then the code is discarded.
The code is started, but you can write something new. I mean, you can write some new code in C in GDB command line.
Oh, I messed up my subfunction 1. I'm going to write a new subfunction 1 and patch up the symbol table so subfunction 1 is overwritten? Or just new code?
Oh, well, yeah. I think that just, you cannot replace the existing function. I don't think it can do that. But you can just add some new thing.
Okay.
So just say you can just add a new function that calls out the function. That should be okay. But it is not like the Visual Studio that you can replace a function, the hot function.
Yeah, I was wondering if it was going to go that far.
I'm not sure.
Okay.
Yeah.
And do you have anything to say about kernel awareness?
Sorry?
Kernel awareness?
Okay. So probably I can talk about more about it. Kernel awareness is that is the GDB feature. So nowadays when GDB is debugging Linux, so GDB doesn't understand the task structure inside the Linux kernel. So GDB cannot show anything useful about the Linux kernel threads. The goal of this work is to make the GDB be aware of the kernel threads inside the kernel when you are debugging Linux kernel. So after that, if you type info threads, it will show maybe 20 or 30 or threads in GDB.
Is it to debug the kernel, the Linux kernel itself, or to show information from the data structures in the kernel that are relevant to the process to the user process being debugged?
So far, from my point of view, I think I don't want the GDB kernel awareness, at least in current stage, to touch anything about the user space threads. No, just focus on the kernel threads.
Actually, we can do the probe or trace on the inside the kernel on x86, but currently it seems like ARM64 doesn't support the K-probes or something like that. So nowadays, PathTools support to set up the trace point everywhere in kernel. So you can trace every local variables or global variables in the kernel via ftrace. I mean that ftrace in kernel. Yeah. So I think if we if we implement that K-probes on ARM64, we can do that. So yeah, if you mean that debug as a changing that the local variables or something like that, it's impossible currently. However, if you just monitor or trace the behavior or code paths on the kernel, you can do that.
I've used, kernel awareness on other debuggers, and it usually means, I stop at a system level, and in a GUI, okay, I'm stopped, I'm in the kernel, or I'm in this user process, or this thread of this user process, and I can see the, what the other threads are doing inside that user process. So it's sort of system level, and I can, it's core level at least, right? So this core has stopped, tell me where I'm at, and it can actually tell me where I'm at from a system level.
Okay. Yes, I think this work will be done by Karen, so I leave this Karen to answer your question.
Hey, so yeah, at the moment, the idea is just to get better overview of what the kernel is actually doing. So currently, if I'm connecting with a JTAG, you hit stop, you're stuck in that one process, that's all you can see. So what the idea is so that you can present all of the processes that are running, and say you've got a deadlock somewhere, you're going to stop wherever it's locked, but that's not where the fault is. You want to know who's blocking elsewhere. So, just to be able to switch threads, switch processes, go have a dig, find out what's really going on, and that's where it was useful to us. It's trying to be brought out from work that was done at ST Microelectronics, and there was quite a lot of extensions done there, and we're trying to push them up and make anything that's useful we're trying to get out. Some of the extra stuff is actually being written as Python scripts, and that's been pushed into LKML already, so contact me if you want any more information or try it out or help.
Any questions? No. Okay. Thank you.